Lagrange was of French and Italian descent. Lagrange was one of the creators of the calculus of variations, deriving the Euler-Lagrange equations for extrema of functionals. He extended the method to include possible constraints, arriving at the method of Lagrange multiplier. Now let's start with a question. What is this Lagrange multiplier and when do we use it? So let me try to put this up first. So then you will see this Lagrange multiplier and when do we use it in real life? Okay. I would like to have someone to read this if you're able to see this. Okay. Are you able to see? I also put it up in the Quanto file. So what happened here when you design a pill and the way that the pill's coding decay is considered at all points of the coding surface, okay? The maximum minimum value of the rate of decay can use Lagrange multiplier. And when do we use it? Isaac, could you read the first paragraph over here?
A cardboard box to use a fixed amount of material. To maximize the box's volume, engineer maximizes the volume function subject to constraint the amount of material used to displace it.
Okay, great. All right, so you can find the dimension to maximize the box value, right? And you can use Lagrange multiplier to find the maximum. Okay, the second paragraph over here, I'd like to ask.
Compare an article engineer has to maximize the distance of the object traveled. How the verb is about to be Lagrange multipliers can be used to find the maximum value of the distance from chain given that you think that the amount of fluid is.
Okay, you read the last one.
The production of a product is the amount of labor used and the amount of capital invested. This is standard and use Lagrange multipliers to maximize production subject to certain labor, capital.
Great. Okay, so we use Lagrange multiplier. Okay, those are some examples of how we use Lagrange multiplier in real life. Okay, so now we're going to talk about what is this Lagrange multiplier and how do we use it. Okay, in an example in our last section, we have a box and then we have the dimension for the box will be x, y, and z. Okay, those are the dimensions. And at that time, we are trying to maximize the volume for the box. And this box here has open top. Okay. At that time, we're trying to maximize the volume of this box over here with a constraint. What kind of constraint does it have? The constraint that we have is the surface area has to be equal to 12 square meters. In other words, 2xz plus 2yz plus x times y is equal to 12. At that time, what do we do to find the dimension that maximize the value for this box? You can remember? We first express this function here as a function of two variables. Okay, for example, only x and y, using the other constraint over here. And then, once this is a function of two variables, we find the critical points. How do we find critical points? Do you guys remember? We take partial duality and set them equal to 0 to find critical point. And then we can use what kind of test to find maximum? Yes, the D. So that was part of the second duality test, right? The second duality test to find the maximum mean, okay? So that's what we did last time. But then in this section, we're going to learn a new method. It's called the Lagrange multiplier. So this kind of method is going to help us to find extreme value. Now, notice that this function over here is a function of three variables. To visualize function of three variables, we need 4D, right? So how about we start with a function of two variables first, because we can visualize it by graphing it, okay? So now we're going to explain the basic of Lagrange method for function of two variables, because that way we can graph it. So we will start with this function, f of x comma y, and we are trying to maximize this, okay? Maximize or minimize it, okay? We're trying to find the extreme value of this function. And then we have a constraint, okay? Well, we are going to put on a constraint on that function, and that is g of xy equal k. Just like this example over here, right? We're trying to find the extreme value of the volume, and then we have this constraint. The surface area has to be this. So this is similar, okay? And now let's look at a picture over here. So what do we see over here? On this side over here, you see this picture over here. This is going to be the pink one. Those pink curve over there those are the level curve. Okay? Those are the level curve of the function f. The function we're trying to find the extreme value of this. Okay, and so setting the function value of f equal to different number, and we get those level curve down on the xy plane. Okay, those are the pink one are the level curve. The function value will be 7, 8, 9, 10, 11, etc. Now, and then we have a constraint function, which is g of xy, okay? And that has to be equal to a constant, equal to a k that we pick, okay? So the blue one over here is the level curve for this g, when g equal to k, okay? And what happened over here is that if you try to maximize this function f, okay, and satisfy this constraint g equal to k, what do you think the maximum value of f here is? Can the maximum be 7? Well, cannot, because look at this. The 8 over here, when the function value equal to 8 or 9, we have other points on the level curve that satisfy this constraint, right? This one has 2 points satisfy it. Those are bigger than this. So we had to increase the function value of f until the level curve of the function is going to intersect with this constraint over here at only a single point, that way. Because if you intersect at 2 different points like this, you can actually go further. You can find another, for example, like this one and this one. Like this one and this one. Okay. You might think, well, could this be the maximum for the value of this function f that satisfies this constraint? The answer is no, because here you intersect 2 points, and then you can go further. And you go further, and you have this level curve here, only intersect this constraint curve over here at one single point, then this function value over here is the maximum. Okay? Because if you get further, then that is not going to satisfy this constraint anymore. And this is the one that's satisfied this constraint, and the function value is the highest. So that's the one. So what does it mean to find the largest value over here? So the larger value of this function f is to find the level curve of this function f that is going to intersect this curve over here only once. Okay. Now what happened at this curve that they just touch each other? When they just touch each other, what happened to the tangent at this point? Do they have a common tangent over here? What do you think? Yeah, they have a common tangent over here, right? Okay. So I have another graph over here. So you see that when they touch each other over here, and they will have a common tangent line, this purple one over here. And what happens is when they have a common tangent line, then that means the normal line for this, for both curve over here, will be the same at this point, right? The relation between normal line and tangent line is this. This is the tangent line. Normal line is perpendicular to the tangent line at this point. So this level curve of F and this constraint level curve for the G, they will have the same normal line over here. Okay, they have identical normal line at this point. Do you agree? Then what happened to the gradient vector? What happened to the gradient vector at this point? For the gradient of F at this point and the gradient of G at this point, what can we say about it? You can remember gradient? What's the gradient? Okay, let me remind you gradient, okay? So gradient are orthogonal to level curve and level surfaces, okay? So over here, we have this level curve over here and here. The gradient is going to be orthogonal to those level curve, okay? So now so that will be in the direction of this normal line over here, right? Now, because they have the same normal line, then the gradient of F and the gradient of G, what can we say about the gradient of the F and the gradient of G? They will be pointing in the same direction, right? They'll be parallel, okay? So when they're parallel, then what happens when two vectors are parallel? They'll be scalar multiple of each other, right? So it's like a constant times the other vector, okay? So let me draw this. So if you have a vector going this way, or you have a vector going maybe either this way or this way, when they're parallel, okay? Then what happens here is, say this vector v1, this is v2, then these two are scalar multiple each other. So that is going to be, let's say, c times 2. So it's a scalar multiple each other. So we can see that over here we're going to have the gradient of F and the gradient of G. They are parallel, okay? They're in the direction of this normal line over here, okay? And because they're parallel, they will be scalar multiple each other. And what kind of scalar we want to use to represent here? They use this called lambda. So lambda times that, okay? So this is what we have over here. We have the gradient of F and the gradient of G. They are scalar multiple each other, okay? Gradient F is lambda times gradient of G, okay? Now this is for function of 2 variables. What about function of 3 variables? The situation is very similar, but it's very hard to graph. So what do we do over here is, if it's a function of 3 variables, instead of level curve, we're going to have level surfaces, okay? So imagine those level curve over here are level surfaces, okay? And you graph them, okay? And then you have this constraint over here. Constraint is also called a side condition. So how to satisfy this side condition? Then what do we do? So imagine this is also a surface, the blue one over here. And those are level surfaces. And you also like these 2 surfaces, you find the maximum or minimum, okay, by looking at where the level surfaces is going to just touch this constraint surfaces, okay, similar. And instead of this tangent line over here, think about as a tangent plane. They're going to share the same tangent plane over here, okay. Now, if they share the same tangent plane, then the gradient of F and the gradient of G will point the same direction at this point. okay? Because let me remind you right here. Gradient are perpendicular, or usually we say they're orthogonal to vector and tangent. Okay. So because the tangent plane is defined as the plane that the normal of that plane is the gradient. Okay. So that's how tangent plane is defined. Okay. Now let's look at the picture here. See over here, at this point, this is the tangent plane. And the gradient vector is going to be perpendicular to this tangent plane. This is the gradient of it. Okay, gradient vector is always perpendicular to the tangent plane. Okay, and tangent plane is defined as a plane that is the normal vector is the gradient. Okay, so if we can try to extend this condition for function of 2 variable to function of 3 variable, we get a similar conclusion. The gradient of f and the gradient of g will be parallel, and they will be, and this condition here is going to hold. Okay, gradient f and gradient g are scalar multiple each other. Okay. Now after all this, I think that one of the important things for you guys to remember is this. Okay, so if the gradient of g is not the zero vector, okay, if it's zero, multiplied by any scalar will be zero, so that is not going to it's not going to work. Okay, so if the gradient of g is not zero, okay, then what happens? We're going to have a number lambda. Think about the lambda here like a constant, a scalar, okay, such that the gradient of f is equal to lambda times gradient of g. Okay, and that's the important thing to remember. That's the key idea. So what does it say? So this says that if we try to find the eigenvalue of a function f that satisfies the constraint g equal to a constant, then the gradient of f will be equal to a constant multiple of the gradient of g. Okay, and what is this lambda? This lambda over here is called the Lagrange multiplier. Okay. Okay, so now we say, now I know what's the Lagrange multiplier, but how can this help me to find the eigenvalue, right? Okay, so next we're going to outline the procedure. Okay, and we're going to also use example to see how do we use this Lagrange multiplier to find eigenvalue. Okay, here's the outline of the procedure. Okay, to find the maximum and minimum of the function f, okay, subject to this constraint. Okay, now this is the function we try to find maximum or minimum with. Okay, the function f, and then the constraint is g of this is equal to k. Okay, assume that the gradient of g is not zero, then what happened here is the first step is to find all values of x, y, z, and lambda such that the gradient of f equal to what? You guys remember? Equal to what? Gradient f equal to lambda times gradient g, right? Yeah, you guys got it. Good job. Okay. Okay. And so this is one of the equation. This is actually equation that you need to solve. So you can solve for x, y, z, and lambda. But then we have 4 variables, right? We have x, y, z, and lambda, okay? And we also need to put this equation in, okay? This is a constraint. Remember this one? This is a constraint. Okay. All right. So that is the first part, okay? So basically, try to set up equation to find x, y, z, and lambda, okay, and use this tube. Okay, so I say, oh, there's only two equations. Actually, this one over here can sit as two equations. Okay, we're going to do that. And then press this one, we should have four equations. Okay. Okay, so that was the first part. Okay, so basically the idea is focus on this tube. Okay. And then the second part over here, after you find those x, y, z, and lambda, then you try to evaluate the function value at all of those x, y, z, okay, all of those points, x, y, z. And then whatever that is the largest will be the maximum, and the smallest will be the minimum. Okay, that's how you find the constraint. Okay. Now, here explain that if that is a function of three variables, the first one, okay, this one over here, this actually break it into three equations, okay, because the gradient of f is lambda times the gradient g. The gradient of this, it has three components, right? So the first component will be partial derivative with respect to x, right? And then partial derivative with respect to y, and then the last component partial derivative with respect to z. And each one of them, each component will be lambda times the partial derivative, the corresponding partial derivative. Okay, so that's why it's actually three equations over here. Okay, and then together with this equation, we have four equations, and we have four unknowns, x, y, z, and lambda. So we'll be able to solve the system of four equations. Okay. A lot of time it's not necessary to find the lambda, but all we care about is the x, y, z, because as you can see over here, the second step, you will try to find the x, y, z, and then you will evaluate the function value at the x, y, z, right? So sometimes not necessary to find the lambda, okay? But focus on the x, y, z. Question here so far? Okay. Now let's try to do this. Now that was a function of three variables, right? Function of two variables is similar. So we're going to have to solve x, y, z so that it satisfies this. The gradient of f is lambda times the gradient of g, and then also satisfy this constraint equation. Now, because this is a function of, because f and g are function of two variables, then that is going to break it into, this one here is going to break into two equations, okay? So when the gradient f equal to the lambda times gradient g, then the partial derivative with respect to x is lambda times the partial derivative of g with respect to x. And similar for this, okay? And then for this, you just need to solve those equations to find x, y, and lambda, okay? So the idea is actually not too hard, okay? How about we try to do some example? Let's look at the first example. That was the example we have done last time. At that time, we're trying to maximize the value for the box with the constraint that the surface area is 12 square meters, right? Okay. So I have a box over here. I label them. The dimension will be x, y, and z, okay? And the first thing to do is we try to maximize the value. So let's express the value here in x, y, z. So what does the value equal to? X, Y, Z, right? So that's equal X, Y, Z. Okay, and then you also want to write down the constraint, right? The constraint over here is the surface area of this box, remember without the top, okay, is going to be 12 square meter. So each side will be double except the top, the bottom, right? Okay, the bottom is, so how do we write the surface area for this box over here? The outside surface area. Yes, you got it, okay? Yeah. Right, and that's equal to 12, okay? So you write down the function that you try to find eigenvalue, and you also write down the constraint, okay? Now we're going to use the method of Lagrange multiplier. We try to find x, y, z, and lambda such that the gradient of this v is lambda times gradient of the g, right? Okay. Okay, if I have gradient of this v equal to lambda times gradient of g, then we're going to look at each component. The partial derivative of v with respect to x should be lambda times what? Partial derivative of g with respect to x, right? Okay, etc. Right? So we're going to have this. So the partial derivative over here will be, they are scalar multiple each other. It's going to be lambda times the corresponding partial derivative, right? Okay. Now we have this one, and we also have this constraint, right? So this one here is the one that we have, and then the constraint one is this one. This is a constraint one. Okay, and this one here come from this one, right? Now all we have to do is to find this equation and then try to solve for x, y, z, and lambda, right? Okay. So they all boil down to solving those system equations. Okay, let's do the first one. Can you guys tell, okay, just looking at this, can you guys tell me what is partial derivative v with respect to x? YZ, okay? So YZ, okay, and then lambda times, what's partial derivative g here with respect to x? 2z plus, this one here will be 0, right? And then this one here will be, what's partial derivative this with respect to x? Y. So 2z plus y. So we're going to have yz equal to 2z plus y, right? Okay. So that's the first one. Yeah. So we have yg is equal to lambda times 2z plus y. Remember the lambda over here is just the lambda, okay? Similarly, partial derivative xyz with respect to y is xz, right? So you're going to have xz equal to lambda times 2z plus x. Okay. What's the last one? Partial derivative with respect to z. So this one is xy, right? So xy equal to lambda times partial derivative of g with respect to z is going to be 2x plus 2y. So you have this. So you got the 3 equations. And remember, we need one more equation, right? Okay. So those are the equations that you got by setting those equations come from the gradient of f is lambda times gradient of g, okay? So this one over here, where does it come from? It comes from gradient of f equal to lambda times gradient of g, okay? So you get this 3 equation. And then we're going to use this three equation together with this constraint equation, right? This one. This is the constraint equation. And then we should be able to solve for x, y, and z. How would you like to solve for x, y, and z? There's no very clear guideline how to solve the system of four equation. Usually, a lot of time we try to, one way to do it is, one way to do this, okay, can you guys think about some way to do it? How would you like to solve this system of four equations? Huh? Use measure? Oh, matrix? Four equations. No. That might be an idea. Maybe you can put it in the discussion. How did you solve this using matrix, okay? But without this, how do you do this? Okay, what do you observe over here? This is yz, xz, xy. If I multiply this equation over here by x, if I multiply the first equation over here by x, okay, let's say I multiply this by x, right? If I use x times this first equation, so do I get x, y, z on the left side? It's a little bit light, so maybe. So if I multiply that by x, okay, then I'm going to get x, y, z on this side, right? It's kind of small. Let me make it larger, okay? And then what about the second equation? I can multiply this equation both sides by y, right? And I also get x, y, z, right? X, y, z, x, y, z, okay? And then multiply the last equation here by z on both sides. I also get x, y, z on this side, okay? That way, so if you see something, a pattern like this, you say, okay, maybe I can do this. So all of them has x, y, z on one side. And that way you can equate the right side over here, right? So that's one way to do it. Another common way to solve those equations is you try to isolate the lambda, okay? So you can solve for lambda. So lambda equal to this over this, lambda equal to this over this, and then after you solve for lambda, you can set them equal, okay? So that's another way to do it, okay? So for this equation, you have different way to do it. So this is just one way to do it, okay? I think isolating the lambda and then set them equal is actually a very common way to solve this kind of equation, okay? So keep that in mind in your homework. A lot of time you will just isolate the lambda and set them equal, okay? Okay, now continue with this problem. This time we choose, because the pattern here, this one has yz, this one has xz, this one has xy. So we want to multiply each corresponding equation here by x, here by y, by z, so that we get x, y, z on the left side. Okay, by doing this, what can we say about this quantity and this quantity? They'll be equal, right? They'll be equal. Do you agree? Okay. So by doing this, and this, they're equal to each other, right? They're equal. And then also this, they're equal. They're all equal to x, y, z, okay? Then that is going to help us to solve the x, y, and z, okay? Now looking at this one, I'm going to make it larger. If these two are equal, what happened? Well, either lambda equal to 0 or this equal to this, right? Okay. Or 2xz plus xy equal to 2yz plus xy. Okay. Do you agree? Okay. So we're going to have this. Either lambda equal to 0 or this equal to 0. But it says lambda does not equal to 0. How come lambda cannot be equal to 0? If these two are equal, either lambda equal to 0 or these two are equal. But it says lambda couldn't be equal to 0. Why? What happens when lambda equal to 0? Yeah. If the lambda equal to 0, then this whole thing equal to 0, then the value equal to 0. And then we won't have a box, right? We don't have a box, okay? The value will be 0. So lambda couldn't be 0, okay? So if lambda couldn't be 0, then 2xz plus xy equal to 2yz plus xy. So canceling the xy, divide both sides by 2, we have xz equal to yz. And we know that x, y, z, none of them have to be 0, right? If x or y or z, if one of them equal to 0, we have a 0 value, right? So z couldn't be 0. So what can we say about x and y? They're equal. So x equal to y. Okay. So we have x equal to y from this. So we have x equal to y. Where is it? Here. X equal to y. Okay. And similarly, when we set this two equal, lambda is not equal to 0, what do we have over here? Let's do the algebra. So we'll have 2yz plus xy equal to 2xz plus 2yz. And we can cancel out this 2yz, right? Okay. And then we can divide both sides by x. And what can we say about the y? Y is equal to 2z, right? Okay. So y is equal to 2z from this. And from above, we just talked about that we got x equal to y, right? So we get x equal to y. We also get y equal to 2z. So put them together is going to be x equal to y, and then that equal to 2z, right? Okay. Now after you get x equal y equal to 2z, how do you? Let's go back to this. Which one we want to use to solve x, y, z? So once you have this one, you're going to pack this back into the constraint equation, okay? Put it in here. So you're going to substitute x equal to y equal to 2z into this to eliminate, okay? To eliminate, I think we should maybe just keep the x, okay? So what do we have here? If I want to keep the x, what do we have? So we have 2x, x is 2z, right? So, okay. Oh, I think it may be easier to keep the z. The reason here is because that will avoid some fraction, right? X is equal to z. So let's keep the z. Keep this in terms of z. So this one here will become what? 2 times 2z times z, and then 2 times 2z times z plus 2z times 2z, and then equal to 12. And looking at this equation, that is going to turn that into this equation over here. So you're going to have 4z squared twice, and sum that up equal to 12. And when you solve this equation, you're going to get z is going to equal to, well, you're going to get z squared is equal to 1. And when you take square root, you don't consider the negative square root. Why? Because z is what? Z is the height of the box, right? Can that be negative? Cannot be negative. So therefore, z here is equal to positive 1. So once you figure out z equal to positive 1, then you can figure out the x, right? X is double that. So x will be 2 and y will be 2. And then you can see the box, okay? So I draw the box over here, and then the box here will have the height to be 1 and the length and width will be 2. Then this box here has maximum value when the surface area is 12, which agree with the result we got from last time in using the second derivative test. Okay. So this is using the Lagrange method. Okay. Question? All right. Do you guys want to take a break? Okay, let's take a break, 10-minute break, and come back. We continue. Okay. Okay. So we continue example 2. Okay. We try to find the extreme value of this function on the circle. Okay. So as you can see, this is the function you try to find extreme value with, and this here will be the constraint. Okay. So remember, this is the constraint. Okay. And we try to find the maximum of this, find the extreme value of this function. Okay, so what should we do? Okay. So we're going to, in this section, we're going to use Lagrange multiplier. Okay. And basically, we will come up with those equation. The gradient of f equal to lambda times the gradient of g, and then together with this constraint, okay, this constraint over here. We're going to make this, well, x squared plus y squared equal 1. That function, we're going to use a function. What function is that? Let's call that g. Okay, so this, we're going to call that g of x comma y, and then that's equal to 1. So we have this function f, and then with this function g. Okay. Now from this equation, the gradient of f equal lambda times gradient g, we can break it down into 2 equations, right? Because this is f is a function of 2 variables. Okay. So the first equation will have the partial derivative of this function with respect to x equal to what? What should I put over here? Yeah, that's equal to 2x. But according to this equation, so that will be lambda times what? The partial derivative of g with respect to x, right? Okay. So let's put it down. Okay. And the partial derivative of this function f with respect to y will be lambda times partial derivative g with respect to y. Okay. And so this is going to break down into these 2 equations. And then we're going to use this 2 equations together with this constraint equation. We should be able to solve for x, y, and z. Okay. So, and some of you already told me that the partial derivative of the f here with respect to x is 2x. So we can write this as 2x equal to lambda times, what's the partial derivative of g with respect to x? 2x. Huh? It's also 2x. Okay, let's see. Oh, okay. Yes, 2x. So in this case, both possibility of f and g with respect to x are 2x. And they're related by this lambda. Okay, lambda times that. Okay. What about this equation? Possibility of f with respect to y is going to be 4y. Okay. And then what's possibility g with respect to y? 2y, right? Okay, to 2y times lambda. Okay. This lambda right here. So we got this two equation. And then we also have this constraint equation over here, x squared plus y squared equal 1. Now we just need to solve for x, y, and also lambda, right? We have three equations. How would you like to solve for those variables? This one here is not too hard, right? Okay. So let's think about this equation over here. From this equation, now one way that this is going to happen, you can actually put them on the same side. So you can have 2x times 1 minus lambda. It's going to equal to 0, right? You can factor out the 2x. Okay. From this equation, we can have what? X equal to 0 or what? Lambda equal to what? 1. Okay. So there are two possibilities. Okay. So from here, let's consider case by case. A lot of time when you do math, a lot of time you try to exhaust all the cases. So let's think about the first case. So how about the case that x equal to 0? Okay. If x equal to 0, okay, then look at this equation. What happened to this down here? You're going to get y squared equal to 1. Okay. So let me write it down. Okay. So if x equal to 0, from this equation of down over here, we're going to get y squared equal to 1 from this, right? From equation 11. Okay, we're going to get that. Then what does y equal to? Do you guys see what I'm doing? I put the x equal to 0 into this equation, and I come up with y squared equal 1. So that's why I have over here. Okay. Then y is equal to what? Plus or minus 1. Okay. So this is actually one of the actually two. Okay, so you can have, so we have one solution. Okay, so xy could be equal to, so this could be 0, and then y could be plus or minus 1, right? So xy could be equal to this. Okay, so this is two possibility right here. Okay, when x equals 0, y is plus or minus 1. Okay, but what about when lambda? Now let's think about the other case. When lambda here is equal to 1, let's see how do we do this. If lambda equal to 1, this doesn't tell us anything, right? But this one does tell us something. If lambda here is equal to 1, then what happened? Yes. If lambda equal to 1, yeah, then 2y equal to 4y, then y has to equal to 0, right? Okay, so y has to equal to 0. And if y equal to 0, then you put 0 in y, x squared is equal to 1, then what does x equal to? X squared equal to 1, then x is equal to plus or minus 1, right? So another possibility here is x could be plus or minus 1, y could be 0, right? So we have actually 4 possibilities, right? 4 points, 4 combination for x, y, right? It can be 0 plus or minus 1, plus or minus 1, 0, okay? Then what do we do? What's the second step when you use Lagrange multiplier? You're going to evaluate the function value, the function f, right? At all those points, x, y, okay? So you can define f of 0, 1, you find f of 0, negative 1, f of 1, 0, f of negative 1, 0. Okay, you're going to find all those function value. Okay, and whatever the largest will be what? The maximum, right? So we're going to find that. And then the largest will be the max. And the smallest will be the mean, right? That's how we do it. Okay. This one over here is not hard to find x. Okay, let's look back to the function f. What is the function f? X squared plus 2y squared. Okay, so we do the math. Okay, let me put the function down here so you can see. F of x y is equal to x squared plus 2y squared. X squared plus 2y squared. Okay, so what does this equal to? So 1, that will be equal to what? 2, and this equal to 2, and then this one equal to 1, right? And this one equal to also 1, right? Okay. So what will be the maximum? Yeah, the maximum over here will be 2, and the minimum will be 1. Yeah, so this is the Lagrange method. I think the most difficult part using the Lagrange method is to solve the system equations, right? That does require some quite some work. But after you find those x, y, and then you can just plug it back into the function f and to find the eigenvalue. Okay. All right. So that was the second example. Now, we would like to take a look at the picture. Okay. So here's the picture over here. So the function, this function f of x, y equal to x squared plus 2y squared. The graph of it is this, what do we call this? Oh God. It's not hyperbolic parabola or something. Okay, forgot. But it's this kind of shape. Okay. Okay, so it's this kind of shape. And then what was the constraint function? So the constraint function is what? G of, let's take a look. The function g of xy is equal to x squared y squared, and we restrict that equal to 1. Okay, that equal to 1. That's the constraint. Okay, and now you can see this x squared plus y squared equal 1 on the xy plane is this. Okay, and this one here, this surface is a graph for this function. And when you project this circle, x squared plus y squared equal 1, onto the surface, and you see this curve over here. You can't see the back, okay? You cannot see the back, but imagine it's a closed curve, okay? It's the projected up, okay? You see that? And we're trying to find the maximum of this function f that satisfies this constraint. So you see that when you project this onto the surface, the largest function value over here, it is 2, here and here. And the smallest function value over here, it is 1. This and a different color. So it is 1 here, and then also on the other side, you see the 1. So geometrically, you see those maximum minimum function value, okay, on that one. Now, you also can see those level curve, okay? So the function f has this level curve that's equal to is this pink one. Actually, they're all pink. And then this one here is the level curve for f. The function value is 1. And what do we have here? We have this constraint function, right? We have x squared plus y squared equal 1. And that is this blue curve over here. And where do they intersect? They intersect at where? Here, 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 and here, right? Those level curve intersect the blue constraint curve at this 4 point, okay? At this point over here, okay, it's going to be, what is the x coordinate for this one? If you take a look at on this side, what's the x coordinate? That will be what? That will correspond to this one over here, right? Okay, so that will be 1, 0. Okay, so this will be 1, 0. Okay, and then the other one here, this will be negative 1, 0. This 2, the function value for f will be equal to 1. And those are the minimum. Okay, those are the minimum value over here. And then the other 2 intersection will be here and here. The function value will be equal to 2, and 2 is the maximum function value that satisfies this constraint. You got it? So you look at the intersecting. The level curve intersect with this. Okay, at here and here. And those give you the minimum, and this 2 give you the maximum over here. Okay, look at where they intersect. Okay. Okay, next example, we get lots of examples. Okay, we try to find the eigenvalue of this on this disk. Now, some of you say, well, I think we did something similar like this, but at that time, we have that it was on what? On x squared plus y squared equal to 1, right? But this time, they changed this. Instead, they're going to change this to less than or equal to. So what's the difference? When it's equal to 1, it's just a circle, the pink circle over here. When this is less than or equal to 1, is the pink circle and also including the interior of the circle, right? Okay. Last time we found the eigenvalue on the circle, the pink one. But now if we include the interior, we want to see what will be the eigenvalues, okay? Now, that is going to go back to the closed interval method. Remember, here I put down the review for closed interval method, okay? So the closed interval method, remember in 110A, we talk about closed interval method. This is similar. This is like a closed set, right? Closed set will be a set that include all of its boundary. So each single point on the boundary is included. That's a closed set, okay? So a continual function on this, that's what it says. To find the eigenvalue of a continual function on this closed bounded set, there are 3 steps. The first step is to find the critical point of the function in this set. Okay. So first step, critical point. The second step is find the eigenvalue function on the boundary. Okay. Well, why? Because those eigenvalue can either happen at the critical points inside there or on the boundary. Okay, those are the 2 possible places, inside or the boundary. Okay, inside on the critical point or the boundary. So we only look at the eigenvalue either at critical point or on the boundary. And then after you find those critical points, Okay, you will just compare those function value on the critical point and the extreme value on the boundary. The largest one will be the max, and the smallest one will be the mean. So this is an extension of the closed interval method that we have. Okay. Okay, so now this is a review for the closed interval method. Now go back to this problem and see how we use it. Okay. So did we already found the extreme value on the boundaries, right? Do you find that? Okay. I think which example we did? Let's go back. Oh, just this example, right? This example we did over here, right? So on this boundary, the maximum will be what? 2, and the minimum will be what? 1. Okay. So we know what happened on the boundary. Now all we have to do here is to find critical point inside, and then we evaluate the function value at that critical point. Okay. How do we find critical point? Do you can remember? We take partial derivative and set that equal to 0, right? Okay. So let's take partial derivative of this function. Okay. What's partial derivative of this function with respect to x? 2x, right? What's partial derivative of this function with respect to y? 4y, right? So if you set this equal to 0, x equal to 0, right? Set this equal to 0, y equal to 0. So the only critical points inside the set, right, is what? 0, 0. There's only one critical point, right? Now you just evaluate the function on this point. Okay, put 0 and 0 in x and y. The function value will be equal to 0, right? And then we also got on the boundary, the minimum is 1, maximum is 2. Now we're going to compare them. Comparing this, now you can find the extreme value on this closed bounded set, right? So what is the minimum of this function f on this set right here? 0, right? That's the minimum. And the maximum will be 2, right? Yeah. Okay. Remember, extreme value can only happen at critical point or the boundary, okay? So this is how we find extreme value. Okay. That was example 3. Okay, example 4. Okay. This one over here, we try to find the point on this sphere that are closest to and furthest from this point. Okay. So if you want to look at a picture, I have a picture down here. Maybe I put it over here. I'm going to put the picture up so you can see. Is that my dog? Okay. All right. So now you see. Okay. So this is a sphere. X squared plus y squared plus z squared equals 4. That's a sphere. And that's the point over here. And you're trying to find a point on the sphere that's closest to this point. Does it look like we should have something over here, right? This should, maybe that is the closest point. And maybe another point over here is the furthest point, okay? So we're trying to find those points. So now today we're going to use Lagrange multiplier. So first thing, we want to get two functions, right? The function that we're trying to find maximum value with, okay? What are we trying to find, or minimum? So we're trying to minimize or maximize the distance, right? So let's write down the distance, right? Distance, okay, can you guys tell me what's the distance of any points to this point? Let's say that point of any point in space is x, y, z to this point. The distance here equal to what? The square root of x minus 3 squared plus y minus 1 squared plus z plus 1, this quantity square, right? So that's the distance. Now, the algebra, when you do the algebra with this, when you take duality or partial duality, it will be a little bit hard because it's square root, okay? Now, remember the distance is, so how about we get rid of the square root by squaring both sides? So we're going to square both sides, and we get this. And we argue that if the d squared here is maximized or minimized, then d will be maximized or minimized, right? The bigger the d squared, the bigger the d, right? When d is positive, right? Okay. So instead of maximize minimize this d, we can maximize or minimize the d squared. Okay, now we also think about what will be the constraint. What's the constraint? So this is a function we try to find max and mean. What will be the constraint? G of x, y, z. What is it? X squared plus y squared plus z squared, right? Yeah, that is a constraint. And that has to be equal to 4 because all those x, y, z, okay, all those points has to be on the sphere. So it had to subject to this constraint. So that's a constraint function, okay? So remember that. So this is a constraint. Okay. Now, right now, we just need to do the algebra. So again, we do this. The gradient of f is lambda times the gradient of g, right? Okay. So what is the gradient of this f? Remember, this is a function f. What's the gradient of f? Actually, with respect to x. Remember this one here, we can break it down into actually 3 equations, right? This one here, break it down into 3 equations. So we have partial derivative f with respect to x equal to lambda times partial derivative g with respect to x, etc., right? What's the partial derivative of f with respect to x? Differentiate this with respect to x, what do you get? 2 times x minus 3, yeah, you got it. Okay, and then equal to lambda times, what's partial derivative g with respect to x? 2x, yes, you got it. So you will get 2x times lambda, right? Okay, lambda. Okay, similarly, okay, and then you take partial derivative with respect to y, okay, with respect to z, you get all of this. You get this 3 equation over here, okay? Okay, together with this constraint equation. So the question here is, how do we solve for x, y, and lambda, x, y, z, and lambda? The different way to solve it, okay? Remember, sometimes you can isolate the lambda, and sometimes here in this case, they say that the simplest way is to solve for x, y, and z. Okay, from this one. Okay, look at the first one. First one, what does x equal to in terms of lambda? We can divide both sides by 2, right? X minus 3 equal to x lambda. And then x is equal to 3 over 1 minus lambda, right? Do you agree? Okay, can you guys solve the second one? Can you guys express y in terms of lambda? Y equal to what? Y is equal to, I think is what? 1 over 1 minus lambda, right? And z is negative 1 over 1 minus lambda, right? Okay. All right. Yes. Yeah, this is what they have, right? Here, here, and here. Yes. Okay, now once you have this, then what do? We're going to put this, all of this, into this constraint equation, right? And then we try to solve for lambda. So when we do that, put that in, you come up with this equation. How do we solve this equation then? Looks like all of them have all this change, the denominator is 1 minus lambda squared, right? So how about we multiply both sides by 1 minus lambda squared? Then we're going to get here 9 squared plus 1, that will be 11, right? So 11 over 1 minus lambda squared equal to 4. So 1 minus lambda squared is going to be 11 over 4. 1 minus lambda is plus or minus square root of 11 over 4, which is the same as 11 square root of 11 over 2. So lambda is equal to what? 1 plus or minus square root of 11 over 2, right? Okay, so you got lambda. So once you got lambda, that looks very messy. How do we get the x, y, and z? Oh, then we can put it back right here. Okay, so you can put it back here. So instead of put the lambda there, maybe you can just put the 1 minus lambda, right? That would be a little bit easier. 1 minus lambda is equal to this. You can put it here in the denominator. And then you do the algebra. Do the algebra. Then you get the x, y, and z right here. This is the x, y, and z. Okay. This one or this one. Now, how can I tell which one is the one that closest to that point? Which one is the one closest? Well, which one is this? Not that one. Now, one way to do that, you can think about it in the picture, right? This one here, the x and y looks like has to be positive, right? So it looks like this one here. Another way to look at this is looking at the function f, right? This is a function f. So in order to minimize it, this one here, this is positive, minus 3. And this one here, comparing with this one, looks like this one here is going to give you a smaller value. So I know that this one here is going to be closest. So this point here will be this point. And then this point here will be the furthest point right here. Okay, so you found the 2 points. Okay. So one way is looking at the graph. Another way is you can put those numbers in, and just by reasoning, I think this one here will give you the smallest function value. Okay. Okay, so you see that from the picture. Okay. And then the book also asks you, can you see how to find the coordinate of these 2 points without using calculus? Can you guys do that without using calculus? I actually have to put something down here. Start over here. So this is the point. And we try to find 2 points, right? On the sphere, 1 point is closest and 1 point is furthest. Now let's think about the closest. If it's closest to this point, then it has to be perpendicular to the surface of the sphere. And it has to go through the center of the sphere. Okay. What's the center of the sphere? The center of the sphere is the origin, right? So then we'll have a line over here that go through this point and the center of the sphere. Okay. So once you have the 2 points, so we have the 2 points. If you have a 2 point on the line, can we write the equation of the line over here? What will be the equation for this line? They're passing the center and go through this point. And actually, I put down the review for equation for 9 right here, right? X is equal to x naught plus AT. Remember here, AT, right? Y is y naught plus BT. Z is Z naught plus CT. ABC, those are the component for the direction vector, right? So what is a direction vector? How do you get the direction? You subtract the two, right? Take this one, subtract this one. So the direction vector will be this subtracting this. So that will be this vector over here. This time, inside the parentheses, you use an angle bracket. That's a vector, okay? Once you get the direction vector, you can look here to write the three scalar equation for the line, right? So x is equal to what? This will be a good review for equation for 9. X equal to what? 3t, y equal to 1t, z equal to negative t, right? Okay, good. You got it. And once you have this, you can now remember this is the equation for the 9. So when this one intersects the sphere over here, this point should give you the minimum distance, right? And then the other point should give you the maximum distance. So all you have to do is to find the intersecting point of this 9 with the sphere. So what I'm going to do here is I'm going to plug this xyz into the equation for the sphere to find the intersecting point. Okay, so I plug those into the sphere. That's the equation for the sphere. Okay, and I did the algebra, and I solve for t, and I put the t back, and then I get the xyz. I'll get the same point that we just did using the Lagrange multiplier. This one over here gives you the minimum that will correspond to this point. This point here gives you the maximum that will correspond to this point right here. Okay. So this one here, you actually can do it without using calculus. Okay, just use find the intersecting point of this 9 with the sphere. Okay, got it? Okay. This is a long lesson. My God. Okay, let me finish this today. 2 constraints. Okay. Now, so far we have been doing all those Lagrange multiplier problem with only 1 constraint, right? What happens? You have 2 constraints. Okay. The idea is very similar. Okay, the idea is very similar. This time, the gradient of the function that you try to find the maximum mean is equal to lambda times the gradient of the g plus there's another one, here's mu times the gradient of h. You have 2 constraints, okay, the g and the h, okay. Then this time it's going to be lambda times gradient g plus mu times gradient of h, okay. The explanation is actually stated over here, okay. But now it's going to be a little bit more complicated to solve those equations because now you have lambda and mu. So you will have, if f is a function of 3 variables, you're going to get 5 equations to solve for 5 variables. But the idea will be similar. I forgot, I'm not sure if I assign one homework like this. But if that happens, then you're going to solve this 5 equation. Maybe we go through one example real quick. Okay. Actually, I see a typo in the book. Okay, and I'm going to point it out. Then you guys won't be confused. Okay. So in this example, we're trying to find the maximum of this function on this curve of intersection of this plane and the cylinder. So at this time, we have 2 constraints. Okay. One is this one. And then the other one is this one. So you have 2 constraints. All right. So now instead of so the important part here is just remember this. This time the gradient of f is equal to lambda times the gradient of g plus mu times the gradient of h. And that will bring it into 3 equations. So We have enough time. Okay. Okay, let's just go through this. Okay, step. Okay, so what is the gradient of the function? Okay, take the partial derivative of this function with respect to x, we get 1. Take the partial derivative g with respect to x. This is the g, right? With respect to x, yeah, we also get 1. So this is going to be lambda times 1, okay, and then plus mu. And then you take the partial derivative of this with respect to x, then you will get 2x. So this is the one right here, okay? And then similarly, you get this one and this one. And after that, you just need to solve those system equations, solve for x, y, z, and lambda and mu. But this time you have 5 variables, okay? The process is actually outlined over here, and you can take a look. I also circled the typo. This side here should be minus plus sign. Instead of plus minus, right? This is minus plus. It's not a D. Okay. This if it causes any confusion, remember this is not a D. It should be a minus plus sign. Okay. As you can see here, this is a minus plus. So that's a typo. Okay, just pay attention to that. Now after that, if you want to take a look at the graph, okay. So the first constraint, what is the first constraint? X squared plus y squared equal 1 is one of them. That will be the cylinder. And then x minus y plus z equal 1 is the plane. These two intersect at this ellipse. So this is the curve, the constraint curve. So along that one, you try to find the maximum and minimum of the function value. And you can take a look at this. Okay, this step. Okay, let's do a quick recap of today. Okay, what do we have today? So to maximize the function subject to a constraint is to find the largest value of the function value such that the level curve intersect this constraint curve right here. Okay, and when does it happen? That happens when those curves touch each other. So if you take a look at the graph over here, okay, you see when I see this is the constraint curve here, and this is the level curve. When I move those, okay, when I actually move up and down, you see over here, this is the minimum function value here. And what happened here? This level curve is going to touch this constraint curve here. And then on the other one, when I move this maximum here corresponds to this part here. So touch over here. And another main idea today is the method of Lagrange multiplier to find the maximum subject to this constraint. Okay, that satisfy all this condition. What is part A? Can you guys tell me? What's the method of Lagrange multiplier today? There are 2 steps, A and B. What's step A? Very good. So then you try to find all those x, y, z that satisfy this, right? Satisfy the gradient of f equal to lambda times gradient of g. Okay, and also satisfy the constraint, right? Satisfy the constraint. Okay, what's the second step? Evaluate the function f at all those x, y, z, right? And then the largest one will be the max, and the smallest one will be the mean. So that's the main idea.